Hey everyone, welcome to my channel. In this video, I'll be talking about the problem longest common subsequence. So the agenda for this video is, first we'll understand what a subsequence means, then we'll understand the problem statement, longest common subsequence, and then we'll look into the brute force solution for this problem, and then we'll solve the problem using dynamic programming. Then we'll look at the time and the space complexity analysis for this dynamic programming solution, and finally we'll look at the code implementation for this problem. So let's dive into the problem now. Okay, so what is a subsequence? A subsequence of a string is nothing but a sequence of characters obtained by removing 0 or more characters from the original string. So let's take an example here. The string is Portland. If we don't remove any characters from the string, then we get the original string. So this string is a subsequence of the original string. If we remove, say, one character from the string, say let's say we remove R from this string, so we get this string Portland. So this is a subsequence of this original string Portland. Now if we remove two characters from the string, say we remove R and T, so we get Poland. So this is a subsequence of this string here. Similarly, we can have n number of subsequences. So how many subsequences can we generate for a given string? So here for every character we have two choices. Either we can pick the character or we don't pick the character. So since we have two choices, and let's say there are n characters in the given string, then the total number of subsequences that we can generate is 2 to the power of n. Okay, so now that we understand what a subsequence means, let's try to understand longest common subsequence. Okay, as the name indicates, longest common subsequence between any two strings is nothing but a subsequence that is common to both the strings with the maximum length. So if we take this example here, string S1 as Portland and string S2 as Roland. Now let's start comparing the characters. So let's start from the first character in string S2, R. Is R present here? Yes, R is there here. And O is there here. O comes before R here in this string S1, so we cannot consider this. And then land. So this is common in both the strings. So R, L, A, and D. So this is a subsequence. Also, if we start from say O in this string here, okay. So and then we pick O in the second string, and again land is common to both the strings. So another subsequence is O, L, A, and D, or R, L, A, and D. So either of it. So these two is either of it is the longest common subsequence between S1 and S2. So how do we solve this problem? The brute force solution that we can think of to solve this problem is basically to calculate all of the subsequences for string S1 and all of the subsequences for string S2, and then find the common match with the maximum length. Now what is the time complexity of such a solution? So in order to calculate all of the subsequences of string S1, let's say string S1 has n characters. So the time complexity to calculate all of the subsequences would be 2 to the power of n. And let's say for string S2 we have m characters. So the time complexity to calculate all of the subsequences of string S2 is 2 to the power of m. Now not just that, we have to compare all of these subsequences with all the other subsequences to find the match. So the comparison will take 2 to the power of n into 2 to the power of m. So 2 to the power of n plus m. So this is the time complexity just to find the common subsequence by brute force approach. So can we do better than this? We can cut down the runtime complexity from exponential time to polynomial time by using dynamic programming. Solving problems using DP is actually very simple. With dynamic programming, we split the given problem into smaller problems such that if we can find the optimal solution for the smaller problem, we can find the optimal solution for the bigger problem. So let's see how we can do that. Instead of calculating the subsequences individually for both the strings, let's compare both the strings together. So okay, first what we'll do is we'll split this bigger problem into smaller problems. Okay, so let's say the problem is only the first character in both the strings. Now, if if it is only single character, comparison actually is very simple. So what is the longest common subsequence between these two characters here? It's basically the empty string, right? It's the empty string. Now let's move one character ahead. Okay. Now the longest common subsequence till this point would be whatever we had till here plus the match between these two characters. If these two characters is a match, then we'll add one character to whatever we had before. So let's say the index in S1 is I and the index in S2 is say J. And the longest common subsequence that we had till this point, let's call it as LCS of I minus 1. So this will be I minus 1 and this will be J minus 1, comma J minus 1. So we are assuming that the longest common subsequence till this point would be LCS of I minus 1, J minus 1. In this case, it's basically the empty string. Now, when we compare these two characters here, so this is O and this is O. So there is a match. So the longest common subsequence till this point would be whatever we had till here, that is the empty string, plus this character O, isn't it? So if we want to just represent the total number of characters instead of the actual character, so to represent this mathematically, instead of writing the actual character, we can say we found one extra character when there is a match. So that is basically 1 plus LCS of I minus 1, comma J minus 1, when these two characters is a match. Now let's move one character ahead. So I'll remove this. Now we know the solution till this point, isn't it? So I is here, J is here. Now we know the solution till here. So here these two characters is not a match. So what do we do in that case? So there is a possibility that this character can be a match with this character here, I minus 1, or this character here can be a match with this character here, J minus 1. So we have two possible routes or two possible solutions here. If these two is a match, then we pick this solution. If these two is a match, we pick this solution. If both of them is a match, then we pick either of them. So it's basically the maximum between this solution here and this solution here. That is, the longest common subsequence till this point would be, it is LCS of either this character and this string here. So it is J I minus 1, comma J, or the longest common subsequence between I and J minus 1 till this point. So it's the maximum of these two. So if we want to represent this mathematically, then we'll get the recurrence relation. So let me erase this. So the longest common subsequence at any point I comma j will be equal to 1 plus LCS of I minus 1 j minus 1 if the character at I and j is same. That is, if S1 of I is equal to, if S1 of I is equal to S2 of J. If this is not the case, then it is the maximum of LCS of I comma j minus 1, maximum of these two, LCS of I minus 1 j. If S1 of I is not equal to S2 of j. So this is the recurrence relation. Now we'll use this and solve the problem using bottom-up dynamic programming. So let's see how this works. Okay, so we'll use bottom-up DP, the tabular approach, to solve this problem. So I've marked string S1 here, Portland, and string S2 here, Roland. Now, every cell in this table here will give us the optimal solution to the sub-problem. So what do I mean by that? So if you take this cell for example, the value in this cell will give us the length of the longest common subsequence between string port and string ROL. Similarly, if you take this cell for example, the value in this cell will give us the length of the longest common subsequence between string PO and string RO. So the final result, the longest common subsequence between string Portland and string Roland, is given by this cell here. Now, in this table, I am using one-based indexing just to make things simpler. In the actual code implementation, we'll use the zero-based indexing, the arrays. So this is the recurrence relation that we'll be using to solve the problem. So in the code implementation, we'll do a minor tweak to this because it's zero-based indexing. Okay, let's begin the computation now. The values in the first column and the first row are set to 0. The reason is, if you take the first column for example, the longest common subsequence between string Portland and the empty string is nothing. So all of these values are 0. Similarly, the longest common subsequence between string Roland and the empty string here is nothing. So all these values are set to 0. Okay, let's start with the first letter in both the strings. So this is letter P and this is letter R. So are these two equal? No. So we end up with the second condition. Now the second condition says that the value here would be the maximum of the value in the previous row or the previous column. So either of it is 0, so the value in this cell is 0. Now let's move to the next character in string S2. So this is O and this is P. So is character P equal to character O? This is not true. So again we end up with the second condition. So we compare these two values again and the value here is 0. Now let's move to the next character. This is character L and character P. Are these two same? No. So again we end up with the second condition and the value here is 0. So every value here in the second row will also be 0 because character P does not match with any of these characters. So this is 0, 0 and 0. Now let's move to the next character in string S1. So this is character O. So is character O equal to character R? This is not true. So again we end up with the second condition. So we compare these two values and the maximum of it, either of it is 0. Now let's compare character O with character O. So this is same. So we end up with the first condition. So the value in this cell would be 1 plus whatever we have in the diagonal, I minus 1, j minus 1. So it is 1 plus 0. So this is equal to 1. Now let's move to the next character. So character O and L. So there is no match. We end up with the second condition. So we pick the maximum of these two. So the value is 1. Now character O and character A. So these two do not match. Again we pick the maximum of these two. So this is 1. Character O and character N. So these two do not match. Again we pick the maximum of these two. So this is 1. O and D. Again they do not match. So we pick the maximum. So this is 1. Now let's move to the next character in string S1. So this is R and character R. So these two is a match. So we end up with condition 1. So the value in this cell would be 1 plus the value in the diagonal. So this is 1 plus I minus 1 j minus 1. This is equal to 1. Character R and character O. So these two do not match. So we pick the maximum of either of these two. So since both of the values are 1, we can pick any of them. So the value is 1. Character R and L. So these two do not match. Again, we pick the maximum of these two. So this is 1. R and A. The maximum of these two is 1. R and N do not match. Again, this is 1. R and D. These two do not match. So the value here is 1. T and R, so these two do not match, the maximum of these two is 1, so we pick 1. T and O, they do not match, the maximum of these two is 1. T and L, these two do not match, it's 1. T and A, these two do not match, it's 1. T and N, they do not match. T and D, they do not match. L and R, these two do not match, so the maximum of these two is 1. L and O, these two do not match, it's 1. L and L, these two match, so we end up with condition 1. So the value is 1 plus value in the diagonal, so it is 2. L and A, they do not match, the maximum of these two is 2. L and N, they do not match, so it's 2 here. L and D, they do not match, it's 2 again. A and R, they do not match, the maximum is 1. A and O, they do not match, the maximum is 1. A and L, they do not match, so the maximum is 2. A and A, they match, so the value here would be 1 plus the diagonal 1, so it's 1 plus 2, it's equal to 3. A and N, they do not match, so the maximum of these two is 3. A and D, they do not match, so the maximum of these two is 3. N and R, they do not match, so this is 1. N and O, they do not match, this is 1. N and L, they do not match, this is 2. N and A, they do not match, this is 3. N and N, they match, so the value is 1 plus the diagonal element, this is 4. N and D, they do not match, so the value is 4. D and R, they do not match, so this is 1. D and O, they do not match, this is 1. D and L, they do not match, this is 2. D and A, they do not match, this is 3. D and N, they do not match, this is 4. D and D, they match, so the value here is 1 plus the element in the diagonal, so this is 5. So the length of the longest common subsequence between strings Portland and Roland is 5. So this is the expected output. Now we want the actual subsequence with this length 5. So how do we obtain that? So we do a trace back. So we start from this cell here. Now this value 5 did not come from this element or this element. It came from the diagonal because 4 plus 1. So this character is actually a match. So this is part of the subsequence. So we'll add it to the output. Okay. Now this came from here. Similarly, this number 4 did not come from any of these two values. It came from the diagonal, 3 plus 1. So this character n is part of the longest common subsequence. So now we come here. So this number 3 did not come from either of these two. So it came from here. So this character A is part of the longest common subsequence. And we move here. Character L, this number 2 came from here and not these two values. So this character L is also part of the longest common subsequence. And we move here. Now we have two possible solutions here. So this number 1 came from either this one or this one. We can pick either of them. If we pick this one, we get one solution. If we pick this, we get the other solution. So let's pick the one here. So this one came from this one here. It did not come from the 0. So we go up. Now this one here did not come from either of these two values. It came from the diagonal, 1 plus 0. So it came from here. So this letter R is part of the longest common subsequence. So this is one of the solutions. Now what is the other solution? Okay, or so till here it's the same solution. We found the other route. So there are two possible solutions here, either this one or this one. So since we picked this one in the first solution, we'll pick the other route. So this one either came from this one or this one. Since we have already explored this one, let's explore this one here. So we move here. Now this one did not come from either of these two values. It came from the diagonal. So this character O is part of the longest common subsequence. So the land was common in both the strings. And we are adding O now to this. So, and then we end up to the first cell. So basically the length of the longest common subsequence is 5, this value here, and the longest common subsequence is either this string or this string. Okay, now what is the time complexity for this solution? So the total number of computations is equal to the size of this table. So if m is the number of characters in string S1, then the total number of rows will be equal to m plus 1. And if n is the number of characters in string s2, then the total number of columns is n plus 1. So the computation time is basically big of, so the time complexity is big of m times n. Now this is the time complexity. What is the space complexity? The space complexity is again the size of this table. So we end up with the same equation. So it's big of m times n. I hope it is clear. If you learned something new from this video, please do hit the like button and leave a comment if you like it. Now let's look at the code implementation. Thank you. I hope the whiteboarding helped to understand the problem. So the code implementation is very simple. Here we have a class called longest common subsequence. We are given two strings s1 and s2. We'll calculate the longest common subsequence between these two strings. Here we are creating the object of this class, and we'll call this method find LCS. That will do the actual work. Let's look at this method. So this method takes in both the strings s1 and s2 as input. So initially we'll calculate the length of s1 and store it in m, and length of s2 and store it in n. We'll create a DP table of size m plus 1 and n plus 1. The first row in the table is set to 0, and the first column in the table is also set to 0. Now let's iterate through every character in both the strings. So in the table we'll fill the values from 1, 1. So here we have two for loops to iterate through both the strings, and this is the part where we use the recurrence relation. So here we are checking. Now this is zero based indexing for the strings. So we are checking the character at s1 at caret I minus 1 with the character at j minus 1, s2 at caret j minus 1. So if these two are equal, then we end up with the first condition, that is dp of ij will be equal to 1 plus the value in the diagonal element, dp of I minus 1, j minus 1. Similarly, if these two values are not same, if these two characters do not match, then dp of ij would be maximum of the value in the previous row or the value in the previous column. So this is the actual code implementation. This is very simple. Now let's print this table. So there is a method to print the table. So that takes in the completed DP table, the lengths of both the strings. So we are printing it here. And so there is a method called trace LCS. So that will basically trace the actual subsequence from the completed DP. So here, if you see in this table, so we are iterating from the last element in the table, dp of m command. We are checking if this value is equal to the value in the diagonal plus 1. If this is the case, then we are adding that character to the output and decrementing both the row and the column index. If not, then we are checking if the value in the previous row is greater than the value in the previous column, then we decrement the row index, else we decrement the column index, and then finally we reverse the string that we obtained. So let's run this code. Okay, so this DP table output is the same as you saw in the whiteboarding, and this is one of the subsequences, the longest common subsequence between string s1 and s2. So let's probably try another example. So let me change this to A, B, C, D, and say we'll have B, D, E. Now the longest common subsequence between these two strings should be B and D. So let's run and see. So as expected, the longest common subsequence between these two strings is B and D. I hope it is clear. GitHub link to the code is present in the description below. So if you enjoyed this video, please do hit the like button and leave a comment. Thank you. Bye.